Physical Science, it's Mr. B. We're going to finish up Section 1 today. Remember, the first part of Section 1 focused solely on work, which is force in a certain direction. And now we are going to talk about power and how that is related to work. So work and power are two big takeaway themes from this section. And so first off here we have how are the work and power related? So power is the rate of doing work. So that just means the faster you do work, probably the more power you're going to have. So doing work at a faster rate is going to require more power, which is what I just said. In order to increase power, you can either increase the amount of work done in a given time, or you can do a given amount of work in less time. So power is basically how quickly you can do work. How fast can you apply a force in the direction of motion for an object? So that is what power is. And then they're going to give a little example here that work is required to move snow from one location to another, which some of you this past weekend might have actually had a little bit of experience with that. A person using a shovel and a person using a snowblower can both do the work needed to remove the snow. So again, they're applying a force in a direction. Again, it's the same work. However, the snowblower can do the job much faster because it has more power. And this is just kind of to illustrate what they're talking about here. And of course, they use a little frail old lady over there for the shovel and a younger looking guy over there with the snowblower. So I think they should probably switch roles there to make this a little more fair. But because the snowblower can remove more snow in less time, it requires more power than hand shoveling does. So more power is going to be associated with this snowblower because it can do the job in a quicker amount of time. So more power is going to be needed. And so power is just simply work over time. And so we can easily kind of incorporate our work formula with the force over distance. We can substitute those in, and some of these problems between work and power are going to be really interrelated. And if you can figure out work for one, then you can apply it for the power problem for another. So when using SI units in the power formula, remember work is measured in joules, so that's our new one, and time is measured in seconds, which we should know that. And then our SI unit for power is going to be the watt, W-A-T-T, and that is equal to 1 joule per second, which makes perfect sense when we divide work over time, the joule over the second, and that gives us our power, the watt. So we're going to talk about here towards the end where the watt actually came from, because it actually is named after someone. So just keep that in mind. The SI unit of power is the watt. And so now we're going to do a little bit of a sample problem here, and then you're going to hopefully try some of these on your own to get you some to prepare yourself for tomorrow when we do a couple sample problems. So calculating power, so here's our sample problem. It says you exert a vertical force of 72 newtons to lift a box to a height of 1.0 meters in a time of 2.0 seconds. How much power is used to lift the box? So we have three unknowns here. So the first step is going to be actually writing down what information we were given. So we know what the force equals. We know our force was 72 newtons. They gave us a distance of 1 meter, and they gave us a time of 2 seconds. Okay, so what can we do with all that? So what formulas are we going to need that contains our given quantities and our unknown? So we have our power equals work over time, and then remember, work, going back to 2 videos ago, equals force times distance. So we can substitute force times distance in for work because that's exactly what work equals. So now we can plug everything in. We have 72 is our force, 1 meter is our distance, 2.0 seconds is our time. That gives us 36 joules per second, and then that gives us 36 watts because that is our SI unit for power. So if we look back, is our answer reasonable? 36 watts is not a lot of power, which seems reasonable considering the box was lifted slowly and through a height of only 1 meter. So yes, our answer is reasonable. And so now, for some extra credit, and again, I might, most people don't end up doing this, might end up making this for actually part of your quiz grade, but solve these problems here. So first one says your family is moving to a new apartment. While lifting a box 1.5 meters straight up to put in on a truck, you exert an upward force of 200 newtons for 1 second. How much power is required to do this? So just like the sample problem, probably going to need to plug in force and distance there for your work, and you will easily solve that problem. So again, just write these answers on the top left corner of your quiz, or in the bottom, or on the back if there's more room. Actually, let's just go top left corner, so if that's going to have the most room for you to write the answers to your to these problems, and we'll give you some extra credit points. So then the second one is, you lift a book from the floor to a bookshelf 1 meter above the ground. How much power is used if the upward force is 15 newtons, and you do the work in 2 seconds. So this lifting a book hopefully isn't going to be too hard, but maybe make sure you can solve this problem. Again, I'll give you another little extra credit. And then our last one says you apply a horizontal force of 10 newtons to pull a wheeled suitcase at a constant speed of 0.5 meters per second across flat ground. How much power is used? And so the hint that they're going to give you is that the suitcase moves 0.5 meters per second, and consider how much work the force does each second and how work is related to power. So this one might be a little more kind of a little more steps that you have to take, maybe a little more inferencing than just plugging it in, but you're capable of doing that one. Again, just try, write your answers down for extra credit, and we can even discuss them in class as well. And so to wrap this video up and to wrap up this section, we're going to talk about another common unit for power that is used, and that is horsepower. So horsepower, you've probably heard that plenty of times before. That is equal to about 746 watts. So I usually don't like to put a bunch of numbers on there, but I think that's important. This probably will be on your quiz. I'll ask you how many horsepower make up one, what 1 horsepower equals, how many watts does 1 horsepower equal. So 1 horsepower is equal to about 746 watts. So James Watt, who that can probably think that that's where our SI unit came from, he was looking for a way to compare the power outputs of steam engines he had designed, and horses were a logical choice for comparison as they were the most commonly used source of power in the 1700s. So really, he was comparing literally the engines that he created to the amount of work that a horse could do. So that's where he came up with horsepower, because it was literally, if you could do the work of 1 horse, then you had 1 horsepower. If his engine could do the same amount of force or power as 10 horses, then it had a 10 horsepower engine. Then kind of the same thing here. This horse-drawn plow right here and the gasoline-powered engine are both capable of doing work at a rate of 4 horsepower. Because look, we have 1, 2, 3, 4 horses, and this gas engine getting 4 horsepower. So we might think it's common sense that the term horsepower actually came from the idea of how much power a horse could exert, but again, maybe you didn't actually think about it that way. Maybe you just thought that someone was kind of assuming or just kind of coming up with something they thought was good, but literally, horsepower is compared to how much work that 1 literal horse can do. So I think that's pretty interesting, and that is actually it for our first section. Let me know if you have any questions.